We are recording. Welcome to the evening of Python coding. My name is Jacob, and today I'm going to present to you a library called Prefect. I hope I'm pronouncing it right. So I'm going to show you first the website of Prefect. If you go to prefect.io, you get to the website, and they have several products. One of them is the cloud. I'm going to show you the core. Uh, you do this, you go to the overview and it explains to you things. You can go to the code, but actually it's more important to read the docs. And when you read the docs, they tell you a nice story about negative and positive engineering. I just showed you the webpage, but let me explain in my words what they are trying to tell. And again, I'm not representing them in any way. I'm just trying to show you a library because we show a library here every week. And this time I have code. The code is available on GitHub. I made it available for you. You can go to my GitHub account and download the Prefect demo, and there's instructions how to install it, and everything is available here. I'm going to show you this within PyCharm. I hope it is large enough font and you can see. If not, we'll go to and enlarge it, but hopefully you can see what's going on. But let me tell you first of all the story of what I understand Prefect to be. I'll tell you my own story. I'm a computational disease modeler. What I do is I model diseases, and the way I do it, for example, I model COVID now, and the way I do it is I create a, a website, and I think I have to share my screen. Are you seeing my screen? I believe you're not seeing my screen. Am I correct?
We are not seeing your screen yet.
And I was just showing you everything without everything. So I'm going to share my screen.
You can see a beautiful face. Yeah.
Okay, this was nice. Okay, so I showed you my screen. Now I'm showing you my screen, and no one's telling anything, but here
yes,
it
we
is.
can see your screen.
Thank you. So this is the demo. This is where you can download it. And I'm going to show you again, not number, but the Prefect website. And in the Prefect website, it's prefect.io. You can go and read the docs, and it will tell you the story about negative engineering, which I'm going to tell you now. But let me tell you my story first, and this is the code, and I hope you see it big enough. Can you all see what's written here?
Can you make it a little bit bigger?
I will try. Okay, preferences, and if someone remembers which preference it is.
I think it's in view.
Yeah.
It's
Editor font. Okay, let's make it 20. Maybe it will be big enough. Did it change anything? I don't think it changed anything. Let's try it again. Maybe twice. No. No, but wait a second, there's a presentation mode. I just have to, I think. Is it better? Can you see?
yes.
Yeah, this is much better.
Yeah, we can see it much better.
Yeah, I cannot run it, but I'll switch between this mode. I'll talk about the code later first. Okay, so let me tell you the story. I start telling the story of computational disease model. I'm all COVID. One of the things that I'm doing, the way I model not only COVID but other diseases, is something called microsimulation. It's a way that you actually launch a lot of simulations of what happened for each virtual individual, and then see what happens to them in time. When you do it for 1,000 individuals, it takes fraction of a second. But the way I do it is I run many of those simulations and many times those individuals. I need a lot. I need a small supercomputer now to run, and basically a cloud of computers to run some of my simulations. Now, I've been using, and in the past you'll see libraries such as Dusk, and before this Sunguid engine, and all sorts of powerful tools to actually launch simulations that are big. Meaning, you don't launch one simulation. You basically launch many small simulations. Like each time, let's say 1,000 people, but you do tens of thousands or hundreds of thousands of those simulations, and you run them all in parallel. And when you run those simulations in parallel, it takes enormous amount of computing power. So I started by using the entire field that we're doing. It's called sometimes high performance computing because you need a lot of computing power for this. Um, and to run, and in the past there were many tools that did this. In the older times there were tools called Talk PBS. They were run them in clusters on universities. This is kind of research. But recently, things switched to the cloud, so you no longer have to share the computers with other people. You just rent the amount of computers you need for yourself. You're actually sharing them with other people because eventually on the cloud, let's say one of the cloud providers gives you those and virtualizes those machines. It sits on their hardware, and you don't never know where it sits, but you get all the resources of a machine or all the time, and you see it as if it's your own or a cluster that only you can access. So whenever this paradigm started, new tools started appearing. One of the tools that I've been using is called Dusk, and we had an evening of Python coding on it a while ago. What Dusk does is able to parallelize your code. So you write Python code, and it makes those code go and run on different machines or on the same machines on different processors. It can be a machine with many processors. The way it does this, it launches a lot of processes. So I was using Dust for a long time, and every once in a while the simulation fails. It happens, something happened, the code didn't run, the sky, the moon, and the sun didn't align, and I don't know, something happened, and all of a sudden the code broke. What do you do? Dusk didn't provide a solution. However, recently I discovered a library called Prefect that actually solves this. And interestingly enough, it sits on top of Dusk. Also, it's now used, apparently, the way they describe themselves, and now we get to negative engineering, is the fact that they say if you build software so everything will work right, they call it positive engineering. The world is great. You wrote everything so there won't be bugs and so on and so forth, and you believe in your software and it runs, then this is positive engineering and this is all fine because we want things to work if you design it to work. However, what they call negative engineering is like, okay, what happens if the world is against you and things don't work? What do you do then? So basically, it describes a situation of one of your tasks not running well. One of the programs break. And then what's supposed to do? So let's say you have 1,000 tasks, and if they're all important, and if one of them fails, what happens to the rest? Do you throw it away and retry them all? Do you just do this one again? All of those things are things that it's designed to do. It's also has, and if you something that's interesting, you can also read the docs. There's a library called Airflow that's supposed to orchestrate all sorts of processes running together. They claim to be a competitor to Airflow and explain why they are better in some of their pages. I don't know enough to tell you this way or another, but read their docs and they're nice. So what I'm going to do here in the evening of Python coding, I'm going to show you simple amount of code and show you when to use parallelization and when to use prefect and when perhaps not to use it, and to show you where prefect is strong. So I start by explaining what I'm doing, and I wrote a small program. By the way, if you have any questions, jump in the middle. It's better you jump in and ask me the question in the middle. I'll be able to better explain it. So in this small program, what happens is that I import two things from prefect. One of them is task. It's a function that turns any function I do into a task. This means if I decorate a function, and this is a Python decorator, here it's commented, but if I put it on top of any other function, prefect will consider it as a task. We'll explain later what it means. So, and then flow. Flow is, think about a flow of many tasks happening and being orchestrated in the flow. You just define what the flow of data or information of actually processes, what it's going to be. And once you describe it, later on you can execute that flow. So think about you plan of things happening in the future, and this will happen in the future. And this is something important to understand. There's a concept called lazy execution in programming. The idea is that you said, I want to compute 1 plus 1 or whatever it is. So you put it into a function, but it does not compute. The machine only remembers I have to compute 1 plus 1, or I have to compute that function, and puts it in memory and says, oh, I have to remember to do it. Later on, it will execute it. So this builds, this idea is something that is being used here. So in the flow, and actually, I mentioned Dask before. Prefect by default sits on top of Dask. So you just, Dask is kind of like the default engine for it. I'm also importing several small Python libraries just so later I can manipulate little things. What I'm going to do here, I'm going to do a simple function where I actually compute prime numbers. So let's look at this small little function, and this is, I know that there are beginners in this Python meetup, so I'm going to go line by line to explain how it works. So first of all, I define a function, and the function is prime. The function will return true or false according to if the number is prime or not. And the way it does this is it initializes to prime whether the number is bigger than 1. So initially it says everything bigger than 1. 0 and 1 are not considered prime by mathematical definition. But every number on top of it will be true, because I asked the question, this is a true-false statement. I asked, and this will receive true or false according to the number. So numbers 2 and above become prime, are first considered prime. But then what I'm going to do is I'm going to eliminate all the non-primes by just dividing by all the possible dividers from 2 to the number. Notice that this is very inefficient, what I'm doing here, but part of what I'm trying to do is I'm trying to do inefficient things here. I was trying to buy time. You can do it actually to the square root of the number and it will be more efficient. But so I'm looking at all possible dividers and checking whether the number, its modulo, the possible divider, is equal 0, meaning that there is no reminder after the divider. If there is no reminder, then I set prime to be false, because I know there's at least one divider. So this is at the end, I return prime. If any number up until that number didn't divide it, then it's prime. Remember, we set it true at the beginning. So this is the function that does this, and I'm doing it very inefficiently. But oh well. Let's look at another function. The other function I'll be using is only primes. And this is nothing to do. Notice so far I have not even touched anything to do with prefect. The prefect part will come later. Only primes will do the following. It takes the prime vector. I'm giving a is prime vector. I'm giving a bunch of numbers, and I'm asking it, give me only the primes in that vector. Okay, so what it will do is it will look for all the numbers. One more thing, sorry. Is prime vector is something that will be created by is prime. It will be chosen and it will be vectors of ones and zeros. So basically, later you will see I'm basically filtering all the primes out. And the way I'm going to do it is I'm going to look at the number. The number is actually an enumerator. I'm not sure how many people are familiar with enumerators in Python, so I'll explain. Um, if you write in the for loop something like this, enumerate is prime vector, then it looks at the vector, and for each number and for each element there, it will put in a num. So the first one will be the first element will have 0, second element will have 1, third element will have 2, and so on and so forth. So this is like kind of a counter, and the counter will be the number. Is prime number is a vector I plug in that will say whether the number is true or false. Okay, and I'm gonna in Python you can write all of this becomes a big list. It generates this for loop generates numbers and keeps only the prime numbers there. So if the numbers is prime, if I know that is prime vector is a vector of true and falses, whether the position is a prime or not, and I will get a number back a set of numbers that tells me whether it's prime or not. We'll later can jump on this function and actually see what's happening. Finally, I want to break down into primes. I wrote a function that takes and breaks down everything to primes. So what I'm doing here is I am running all the numbers that are possible to divide, but only from the primes. So, and while while the number that I'm dividing is bigger than 1, meaning basically it will be true most of the time, only in 0 it will stop. Then what I'm going to do is I'm going to go and figure out if a possible I'm going to go and look at the indices of the possible dividers. Basically, this will be only the primes. I'm going to run it later on, maybe, and talk about it. And as long as the what's left to divide is what was left after the divisions of the number. As long as it's divisible by the possible divider, what I'm going to do is I'm going to create the divider and divide it. So basically, I'm going to go over, I'm going to explain it in simple words instead of going through the code. But basically, what I'm going to do is I'm going to take all the prime numbers that I had and try to divide all of the numbers, the number I'm getting here, by all the prime numbers as many times as I can, and such that eventually I will get a breakdown of all the numbers by the I'll get up the breakdown of the numbers such that it will be only as a multiplication of primes, and in a very efficient way such that I always try the smaller ones first. That it involves 2 while loops. Later, look at the code. If you have questions, send me questions. It's maybe not the most efficient code, but it's something that does the work. You will see it in action in a second. So eventually, it will look and tell you if the number, if there were no dividers in divider list is actually each time you find something to divide by, then it will add it to the divider list. If the divider list is 0, this is a special situation where you have a special number that is not a prime, like 0 or 1. But the divider list should be at least 1 because the number always kind of divides itself. So this is how I decide it's a prime. And else I can give you all the dividers list that creates the number. This is by output string. So break down to primes, breaks the number into primes, and gives me back a string to tell me whether the number is a prime or not. The last thing I'm going to do, and ignore this task for a second, this is prefect, but what I'm going to do is I'm going to output to file. I have a bunch of strings from a starting number and the lines per file. So the start number is like I want to start in number 50, and then lines per file. If it's 50, it will show me all the output strings from 50 to 100, or from 50 to 99. This is what will happen here because I'm starting in number 50 and I'm asking for output for 50 numbers. So, and it will drop it into a file name that starts with 0, 1, 2, 3. It depends on the number. On the number of the file, so the start number. So it tells you, sorry, not 0, 1, 0 and the start number. So in case of 50, the first one will be, the first 50 numbers will be prefix demo 50, 0, then this next set of numbers will be prefix demo 50, and so on and so forth. Basically, it shows you, it just breaks it into multiple files. I'll explain why I did this later. Let us first run the code and see what happens. And I'm going to minimize it. I apologize, but I'm going to minimize it back after I run it. But first, I'll explain what's going to happen. The main code, what it does, it runs max numbers up to all the numbers to max number is the last number that we want to actually calculate prime to. Actually, last number minus 1. So we want 20,000 numbers starting from 0. So it will break us, and I want the files to be broken into 5,000 to blocks of 5,000. I want each file to contain 5,000 numbers that are prime. So later you can locate your number and see whether it's prime more easily. I'm going to skip those. Those are in case we define system arguments. We're not going to use it here, not now at least. I'm going to ask for how long does it take. This is where prefect starts. I'm going to skip it for now. Just I'll explain the prefect part at the end. When I'm running the code now, I'm going to check whether it's a prime number. I'm going to check whether all those numbers are a prime number. How do I do this? Range index to max number creates a vector of all the numbers, and I'm going to run over all the numbers and just calculate whether it's prime or not. And then I'm creating a file of now a parameter that tells us whether a number is prime or not according to the position. So in position 0, it will tell me it's prime. Position 1 tells me it's prime, and so on and so forth. Okay? And then position 2 will tell me it's prime. Position 3 prime, and so on and so forth. 4, it will tell me no, it's not prime. So this is what it is here. And then it's just a statement that I passed it. Later on, I'm going to compute only prime numbers. I'm going to just run the program that looks at all this vector and returns to me only the prime numbers from this vector. Remember, the vector tells me whether a number in the position is prime or not. This will return to me the numbers, only the numbers that are prime. We'll need those later. And later on, we're going to calculate the divider strings. So we're going to break down into primes all the numbers ranging from 0 to max number. And we're going to get all the divider strings, which tells me how do you calculate each prime. I'm going to show them to you in action, and you'll actually see that. And finally, I'm going to divide this into files. I'm going to ask the system to create a vector for each file number that's in the range of max number. The ranges start from 0, and then each max lines per file up until max number, it will create me a file number. And I just output it as a vector. Now, it looks funny. It's not the for loops you're familiar with, because instead of writing for loops, I'm putting everything into vectors. It's kind of funny to comprehend for people why I'm doing it at the beginning, but this is the way you parallelize things. You don't deal with for loops anymore. You put the for loops into vectors and ask the machine do things vectorized. So I skipped the flow and I skipped some other things. Uh, I'm going to run the entire code now, and hopefully it's going to run now. And I'm going to run it in debug mode. Hopefully it's possible. Oh yeah, I can run it in debug mode here. So what I'm going to do is I'm going to just put a breakpoint. And if I can, here's the breakpoint. Did I put the breakpoint here? You know what, I'm just going to run it up until here. So you can actually run. I'm using the debugger and where is the run to point? Okay. Here, I just stopped it in the middle of something. It's computing a prime, so we can actually see what's going on here. So you can see there's a number, it's currently stuck in 17,000, and I'm trying to figure out, there should be another, here it is. I can go line by line and see what happens. It's now trying to divide it by the number 13,000. So I'm going to step over and it continues. I'm not going to go into this loop. We're actually going to exit this, but you can later follow up with the debugger what's happening. And I'm going to step out for this function. This is when it's computing all of those numbers. And you can see it tells me it's currently doing this number. And I'm going to step over here and run until that point. This is the second, yeah. So it finished calculating the prime numbers, and look at the number. Actually, I'm going to show it here. You can actually go and see. You see? It tells you whether the number is, so 0 and 1 are false, are not defined as prime, but 2, 3 are defined as prime. 4 is not prime, 5 is prime, and so on and so forth. This is what the globe prime vector is. So now remember that you saw trues and falses here. It will be important later. We're going to step over now, and only prime numbers return to you. Only the numbers that are found to be prime. This is the difference between the prime vector and the prime numbers. So for hopefully some of you are with me. Craig, can you make a noise to make sure that I didn't lose you all?
We're so good.
Okay, goody. Thank you. If you have questions by now, please ask before I go to the prefect part. It will mess you up a little bit. No questions on the...
No questions yet.
Okay. So we'll continue to the next one. Now we're going to create the divider strings. We're going to run this. It will take a few seconds to do it because this is something that takes a little bit more, especially the debugger. It takes more time because it's... But eventually it will pass it, and I hope I press the correct... yeah, I pressed that over. Yeah, Craig, you might want to lower your... mute yourself because I'm getting feedback. If it's Craig, yeah. Okay, the divider strings, I'm going to show you what the divider strings look like. Divider strings is a vector that looks like this. 0 is non-prime, 1 is non-prime, 2 is prime, 3 is prime, 4 is equals 2 plus 2. This is the combination of primes. And so on and so forth. 5 is prime. And now you can see what this function does. Later on, you can go back and look at exactly why I did this. It's a little bit convoluted. If you can find a better way to do it, feel free. I was not concerned about efficiency, actually trying to make things as less efficient as possible. But I'm trying to accommodate all of the people, those who are experts who came from the prefect and those who are beginners who want to pick up a little bit of Python and understand what's going on. So this is what I'm showing. Finally, this is where things will become funny. And this is where I'm going to stop and go and introduce prefect. So I'm still in the debugger. Let's go up here. And I'll explain what prefect does And here, I told it when you compute the output to file function, it is not a function, it is a lazy function. How did I do this? I defined it as a task. I'm saying, don't execute it now. Remember it later. The minute I put the task decorator, this is a decorator in Python, for those who don't know. The minute I put decorator on top of the function, this means it does something to the function. In this case, think about it as a function that acts on the function. In this case, task calls this function. The minute I put task, it says, this is a lazy function. It will not be computed on the spot. It will be computed later. And there are some parameters. Later on, I'll talk about those parameters, but this is what prefect does that some other systems cannot do. Prefect allows us to define things like number of retries and what is the delay. So I asked the system, compute this function 10 times, and if you don't succeed, try it again. How many times? 10 times? Each time, try it 3 seconds after the first time. This is what Prefect can do, and this is what its power. Dask cannot do this easily, and other systems cannot do this as far as I know. Well, with programming, you can do whatever you want yourself, but here it comes built in, and also Prefect has abilities to define it a little bit more, a little bit better. So when I actually write the file down, it will not compute it. But to be able to do this, I have to define it as a flow. Why? Because later, all the things under flow, when you say with something in Python, this means all of those commands will be executed under this definition. So with flow, this means as long as those commands, those tasks will belong to this flow. And I gave it a name called prime flow. You can give it your own name. Later on, after we finished defining everything, you remember I talked this is lazy? Nothing gets computed until I tell the system flow.run. So let's see what happens now. Unlike any of the other vectors that I defined, I'm going to go ahead and run only this command. And it's going to go ahead, I'm going to step over. Basically, I could have run it 4 times and showed you each one what happens, but it doesn't matter. Let's look at files created. Files created is not a file. It should, if you go to the output to file, it should return a file name. Instead of a file name, the system tells me I'm not getting a file name. What I'm getting is something else. Files created. Let's show files created. Here we go. You see, it shows me those are tasks. I get 4 tasks to execute later. This is lazy execution. The system doesn't, it's lazy, it doesn't do anything. It says, oh yeah, I have to remember. Now let's go to the next part. And I need to show you the console for that. So you'll see the outputs. This is with the outputs the program printed in. So this is how many times those things took. I'm going to step over now, and I'm going to ask the system, run the flow. Up until now, this has not been executed. It's waiting in the flow, somewhere in the ether. Now I tell him, run the flow. What's going to happen now? Prefect is going to run all those files. And he tells me, it started the process, it runs it, and eventually it tells me I executed everything, and I'm exiting. So far, any questions? Please do ask. If I tell you there's a quiz later, will someone ask a question? Okay, quiet. Great. Make a noise.
We're doing very good right now. I don't see any questions yet.
Okay, good. So I'm going to go ahead now and I'm going to exit this big presentation mode. Everything will become smaller the minute I figure out how to do this. I think this is this way, and view mode back to exit presentation. Exit Okay, and I think I'm still not seeing all of the things I've seen before. And it just minimized this. Um, I need to show you the files that were created. I think. Uh, Anyone remembers in PyCharm how do you bring back the window? Ah, here it is.
There it is.
Yeah, yeah. It's like so many editors, I don't remember which one I'm in. Okay, so you see those files were created and we can actually look at them. Basically, it tells us all the numbers that are prime and whether are prime and which are broken into primes. Pretty easy. And actually, you have a README to help me in PyCharm. All of those files exist. So what I'm going to do now, I'm going to now run the same program. I'm not going to run it in debug mode. I'm just going to run it. And I'm going to show you what happens if I prohibit things from happening. So the way I'm going to do this, I'm in this Python project, and I'm going to open this 0 file. I'm going to just open it in something that will lock the file. In Windows, you can open it with some programs that lock the file such that nothing else can manipulate it. So we're going to open it with LibreOffice. Usually editors lock files, and it's not always. And I'm going to make a change in the file. I made a change so it will just lock the file, meaning no one can open or close or manipulate that file. If a program tries to manipulate that file, it will return an error, and therefore nothing will happen. Now, why do you think I did this? Any ideas?
I think it's to demonstrate that it's because of the flow, it's the lazy part of it, that it's just going to wait until it is available instead of just crashing and ending and having to start over.
Perfect. Yes, good answer. Okay. I have one good student. I'll give you an A, Craig. Okay, so I'm going to run this flow now. And what it does, it will, again, compute the primes, can do other things. And it will take a few seconds, I think like 20 seconds or something like this. Let's see how much. And if you could hear my machine, you'll see it's working hard. But now it computed those two numbers, and then soon it will get to the point that will be blocked by the file being open. You see this error message that tells you, oops, this is an error message. What it's doing now, it tries to, you see, permission denied. It will try it for 10 times. If it tried it for 10 times and nothing happened, it will exit and there'll be an error. What I'm going to do is I'm not going to give it 10 times. I'm going to now close the file. Don't save. The minute I did this, everything ran. Because Prefect tried it again, ran it, and now it ran it successfully. This is the power of Prefect, the negative engineering. What if the user did something wrong to me and something is not working? What to do? This is what Prefect handles. And notice all of those things happened in parallel. If there were the way to demonstrate it properly is to actually show you how much the computer is processing in parallel. However, unfortunately, I have a Windows machine and I had problems installing the viewer that shows you all the tasks running and how many of them are running and how fast things are processing. Dusk has this. Prefect has some other interface that's not the same, and I could not install it. I apologize. I know it installs better on Linux because I've seen it. I had problems in the Windows system. So I will not be able to show it to you, but believe me, all of this, if you have computing power, will happen in parallel. Because what's happening, you're doing all of those tasks become processes or threads. I believe these are processes in this situation because it takes a long time. What I'm going to do now, I'm going to do something funny. I'm going to go ahead and you remember all of this program was written such that everything I compute is vectors and all the functions I apply on elements of the vectors. So this means I can take those comments off and make those into tasks. So now breaking down into primes will become a task. I'm going to show it to you later in the debugger. I'm going to show it also that it's not a good idea to do so because I'll explain later why. But you see, all of those, I just put them as tasks. Those things takes fractions of a second for a computer to compute. Even though it looks like 20,000 is a big number, it takes time. No, it's quick. However, what I'm told it now is no, you run those as tasks. And more than this, when Prefect creates those, it actually will remember that the task graph. It knows that what task has to be computed before other tasks. So I'm going to run it in debug mode again, just to show you the output, how things are different. And I am going to stop here. Here we go. So I put in the Trichet. Actually, not stop here, stop here. This will take a while. But what it's doing now, it's doing all the 20,000 numbers that we computed. Actually, let's not do 20,000. Let's make it something like 200. And let's break it into 50. I want it to be in reasonable time. So we're going to restart it and with smaller numbers.
Side question real quick while it's running.
Yeah.
You said it would fail 10 times and then it would exit out. Is that a default or is that a setting that you selected? Maybe I missed it.
Remember what I did here.
I looked away at one point, so I might have missed that part.
Okay,
thank you.
So you see, the task that I defined, if I don't define any parameters for a task, then it's just a task, just like task. But if I define parameters, then there can be many more. I didn't go into the complexities of Prefect. Prefect can do much more than what I'm showing. I'm showing something very, very small. What it can do is it tells you, okay, we try this. Maximum number of retries is 10. After 10, it will stop. And number of seconds between retries is 3. This is what I chose. We can manipulate those numbers and you'll see it's a little bit different.
Thank you for showing that. Thank you.
Okay, so this is about the task. But notice the other tasks are just tasks. I didn't put any parameters. I don't expect them to fail. But think about complex programs. Things happen. Bad things happen. Things fail. You need to handle this. This is what they call negative engineering. You have to handle the negative stuff. It's not like bad engineering, negative engineering. It's like you have to handle the negative stuff. This is the approach. Okay, so now I'm here, and you remember I now put everything into tasks. And you remember what task does? It makes it such that it's lazily computed. So notice, I got to Glomus prime vector. What it's doing now, it's taking all of those numbers, and I'm going to show it here, Globus prime vector. All of those are tasks. It knows that it's going to compute 100 of those or 200 of those, you see? Actually, 200, it says 99 plus 100 more. So it's going to compute all of those, 200. But it tells me it's a function I'm going to execute. It did not run the prime. It just knows it's going to run it. It also knows that each time you use this globe prime vector, you are can use it in a computation with the other tasks that will feed from it. So, and it remembers the order to execute them. This is called the computation graph. The only prime numbers, you remember before this it was a vector? Now it is a task. Okay? You see, it knows that it's going to compute those over what's other tasks. So it remembers that this comes after all of those have been computed. So think about it, all those clouds of tasks that remember the order of executing them, and it remembers that. Finally, this takes a fraction of a second because nothing has been executed so far. The divider strings are now also Nothing has been executed. It tells me, oh, it's tasks. It's 200 tasks I'm going to execute in the future. But first, I have to execute. I have to remember only primes, numbers, and the global is prime vector. So it remembers the order to execute them, and finally, it has to create the files. And again, it's those files, as before, are tasks. You can show them here, 4 tasks, because it knows. Nothing has been computed, but only the thing, it just made a plan of what to compute. Now it executes the plan, and now see how slow it is. Because what it does, for each one of those tasks, it has like 1,000 of tasks now. It is now going to execute those. And actually, I'm going to stop the debugger. I'm going to do all of this in a second. I'm going to just execute it fast without the debugger. It will be a little bit faster. But now you see it started executing and it finished some of those tasks. Those are the simple tasks. It tells you exactly which one. The task is prime. It has to finish 200 is prime tasks before it continues. Now it continues to the next only primes. It started it, it executed it, and now it starts to break down into primes. If it will execute those in parallel. It will eventually finish and print everything, and all of this has been executed in parallel. However, this was not a good idea. Why wasn't it? It eventually finished everything. It did it all after 17 seconds, but it did much less than the 20,000 that I did before. And the reason is if I give it all 20,000 numbers and 5,000 as we had before, it will take a long, long time. Any guess why? Even though it's parallel. Why? Any ideas?
Because it has to wait for the end of the previous section because it's still going from beginning to end to calculate the prime numbers off of the previous ones.
No, those
No.
things happen in parallel. Think about it. Now, those things, all those prime numbers will be computed in parallel. So all of those 200 numbers, it doesn't have to compute. All of those are not dependent on each other. It will know to execute them in parallel. But still it will wait for a long time. And the reason it will wait for a long time is different. Come on, we have some experts here. Jump in. Our experts are shy. Okay, I won't name them. They'll talk later, probably. Okay, so the reason is because when I run this, what happens is that to compute all of those things, the system has to do a lot of pre-computation, has to prepare an environment, like launch a process. And this is very expensive on the Windows machine, sometimes on a Linux machine box as well. Meaning it takes a lot of time for the system to prepare the environments just to launch something very simple as that. There are ways to speed it up, but in Dask and some other things, I won't go into this. But this is the reason. So the environment setup takes a long time. So think about it. If it would take a fraction of a second to compute this, it may take a second or two to set up the environment to launch it. So this thing, although I have 8 cores on my or 8 virtual cores on my laptop, it will still have to do something much more heavily to compute. This is why it's important to know what things you want to run in parallel and what things you don't want to run in parallel. When I run my disease models, my computations take for each one of those tasks takes about 5 or 6 minutes. So or 10 or something like this. So spending 5 seconds on launching and creating the environment is worthwhile for me, or 2 seconds, or how much few seconds it takes. It's worthwhile to pay because I get, especially if I have, because if I can parallelize things and run them on multiple cores, on multiple CPUs. It's not always the case. In this situation, the computation was too simple. It took the system faster on one CPU just because it didn't have to make all those preparations to launch a task. Did I explain it well?
Yes, it definitely makes sense
Okay.
to me. And I'm seeing a yes in the comments as well.
Okay, in that case, I'll stop the I'll stop the I will stop the presentation now. I'm going to go back to the window that we can talk to each other. And, and if you have any questions, now's the time to ask. Anyone? Okay, no questions. That's unusual. Anything about parallel computation? Anything interesting, maybe not related to prefects? Anything you want to know about parallel computation? We have a quiet audience today.
I do like the concept of it. You know, there's always the error checking and managing for whenever there's errors. This is just a much more advanced way of being able to do it. Or I say it's much more. It's more advanced than the basic stuff that you do as a
Yeah.
beginner programmer. So it's like the next step in it.
So this is why I showed this library. We showed Dask, I believe, last year. This is something I learned about actually last year, and this year I'm showing it. There are other libraries to help with it. Oh, someone wants to ask a question?
Yes, what would be the use cases for this package?
So I gave you one use case. In my if I ran my simulations that take, let's say, I'm running tens of thousands of those tasks. What happens if one of those fails? For example, I ran Monte Carlo simulations depending on random numbers. Sometimes take a random number that define something that is inadvertently will break the simulation, like a division by zero or something like this that I didn't catch before. However, it's not a bad it's not like bad for the simulation. It will just break the code because I didn't think about it. So now the question is, I want to run the same simulation with a new random number, and it will be okay. So when I do this, I want, if I, up until now, if one of those 10,000 simulations that I run, or several tens of thousand simulations that I run, breaks, I lose a whole day of computation. Now, what I do is I say, okay, if you got one of those 10,000 wrong, just fix it, try it again. Give it to me again, and it'll be okay if you give me a different random number. I don't care. As long as they eventually generates results that make sense. And then I have 10,000 good examples that I actually can go on and don't lose a day of computation just because one thing failed. Also, other use cases. Think about things that depend on each other. And let's say somehow a net, some case you need to connect to the internet, and the connection broke. And you have many things depending computation depending on the downloading some data from the internet. Let's say you take new data all the time. Now you can retry this and tell the system, wait for this specific task to finish properly. And if it doesn't, Prefected actually has more advanced method of saying what you do after things don't work okay. Do you do all computations? Do you wait? Do you restart? All of those are things that you can control. I won't go into details. I haven't tried them myself, but they do exist in the documentation. So I urge you to go to the Perfect website and try again and try to understand what the package does. But I gave this small example to explain something very simple what it can do. Did it answer your question well?
Yes, it did. I have another question. Is this using threads?
I believe it uses processes on, especially on Windows. There is this is where you got me to the point that I didn't explore enough. In Dask, there's a way you actually can define whether your workers, the the things that execute your functions are defined as threads or as processes, and how many of them you have. It's also not 100% understanding of, I don't have 100% understanding of what's happening under the hood, but Prefect sits on top of Dask, and there might be a way to define this that I don't know. uh, I I'm just showing you what I know about that library which is very basic. I learned it myself for this demo.
How's the memory utilization?
Huh. Well, think about it. You now have to, instead of each computation that you make, what it does, it just creates those tasks. And it transmits them between something called, in Dask especially, I don't know about Prefect, probably since usually these engines know it's probably the same, it transmits them between the scheduler and the workers. So there is some memory overhead. However, if you need a library to parallelize things, usually your overhead is not the problem. Usually your problem is the fact that you want more CPU, or you want to cut down the things into chunks that are too big for the memory anyway. So all of those overheads that we're talking about are relatively small. In the simple example I showed you, the overhead, for example, of CPU time was very large. So this it actually made things slower. However, it's usually if you need actually to compute something big and you break it into chunks, usually your problems are different than the memory overhead. So I don't believe that the overhead is that significant. Yeah, this is tiny compared to the things usually you want to do. But remember that you do have to transport those things. In Dust, there's a way, sometimes the memory overhead comes to the fact that you have to, or some other overheads have to do with the fact that you transmit the Python code between the workers and the scheduler, especially if they sit on a different machine. There are ways in Dust to make it easier. I believe Prefect has the same. I didn't explore. Maybe, maybe not. Check out the documentation. This is the best answer I can give now.
Thank you.
Um, any more of those questions or others?
Essentially what I'm understanding is the best case uses are dependent on trying to find out what your input of data is. Like if it's just a closed source input of data, like you're just on your laptop and you're inputting whatever, it's one thing. But it's the fact that you're reaching out and you're getting data from different sources, you're ripping it off of a website, maybe they update their website or something. It allows you to adjust for those changes and stuff like that. Essentially,
So,
kind of,
so
right?
the thing is how stable all of your things are. If it's a computation that runs on your laptop, like running something, you can usually, even in Python code, you can do try and accept statements. Or there are other libraries that we actually showed one many years ago. It's called retry. I'm not sure which Python meetup was it, but we had one that shows the library retry, which actually retries the same thing, like in case internet connection fails. Very similar to what Prefect does. However, Prefect does these things, it plans what to do. Think about it as you're making a plan of what to do in the future, and you're also making a plan what happens when things fail. And this is important. This is what it can do better than, like, you have a backup plans and you can actually orchestrate them and say those are my backup plans, and when the time comes, if something fails, you already have the backup plan in place and ready to adjust. So it's not as simple as this. Is what the difference is between some of those. And in simple words, if you're running something on your laptop and it's good enough for you, you probably don't need Prefect, unless it's a special use case or something I haven't thought about. The problem becomes when you run many things that can break or not on your computer, and you need to connect and you need to take data from here and transfer there, and many things can go wrong in the middle, and you have to do this in 2 a.m. in the morning in 3 days, and then something else follows it, and then something else follows it, and five other things follow this and depend on that. This is where you need Prefect. Okay. Um, any more questions? If there are none, I'm going to stop the recording and we're going to go speak as usual. Questions? Going once? Going twice? Going three times? Well, thank you for staying that long. I'm going to stop the recording. And after the recording, stick around. We'll be able to hang around and solve some Python problems. Okay, I have to just figure out how to do all of those stop things.